How many of you have actually played darts before? Okay, so maybe about half the class or so. So if I'm going to sketch this out into a set of 4 dartboards. And now it looks like some kind of weird monster. Oh, like a stove, yeah, I can see that. And I'm going to place my darts on the first one, 3 of them right here, dead center. Okay, so when we're playing darts, depending on the game you're playing, you've got different objectives. One of the games you can play, you're just trying to get the darts as close to dead center as you can. So in this case, we'd be both accurate and precise because we got all of our darts to hit exactly at our target, and they're a very tight group. So this is accurate and precise. Now, when we talk about measurements, if we're just accurate, as you guys pointed out in your daily question responses, that means we're just close to the right value, or close to the correct value. So if I throw my darts and I land one here, I land one here, I land one here, I'm not terribly consistent, but I'm close to my target. I'm almost at the right spot. So I could call this accurate. Now, I could also throw my darts, and this is how I actually throw darts because I'm terrible at the game. And I could land one here, and my next one here, and my next one there. And we would say that that is not accurate because we're not hitting our intended target. However, we could say that it's precise because it's very consistent. So this would be precise. And now it seems like every time I play darts with a partner, my partner winds up being this individual, where they have one here, and maybe the last one's over here. So neither precise nor accurate. And we can correspond this to measurements that we took when we were working with our string lab. So as one of the measurements you guys had to make in the string lab, you had to measure the length of the room. And I looked through the string lab results, and most of us did pretty good. The actual length of the room is 12.17 meters. Length of room. Now, some of you wrote down that the room was 12 meters long. Which one of these boxes do you feel like 12 meters should fall into? Which box do you think 12 meters should fall into? Yeah, Rory. Accurate. I agree. Why do you think accurate? Oh, sorry. You said accurate. Why do you think accurate? Okay, it was close to our target. Good. Now our next measurement, let's say one of the groups measured it at 12.28 meters. Where do we think that one should go? Where do we think 12.28 meters should go? Rory ventured out the first guess for the day, so somebody just got to follow up with the second one. Zane, what do you think? Why do you think precise? Okay. I'm just going to keep going because you got to give me a reason. Okay, I agree with you that it should be precise because it is a more exact value. However, I would also say it's accurate because it's reasonably close to the actual value. So like if we're calling 12 meters accurate, we should probably say 12.28 is also accurate. So I would say that this one is both accurate and precise because it's both close to the real answer and shows a level of exactness. Okay, how about something like 13.065? Where should we put that one? Where would we put something like 13.065? Yeah, Colin, right? So again, up here. Okay, why do you think accurate and precise?
Because it's like going down to like the
Okay, so I definitely agree it's precise. And why do you think accurate and precise?
maybe
Maybe it's just precise, you mean?
yeah.
Okay. Eva, you had your hand up.
Yeah, I was going to say it's only precise
Why?
because it's not close to 12.7 or 12.17.
Okay, so I would agree with that. I would definitely say it's a precise measurement, but it's not really close to the actual answer. So it should probably be over here, 13.065 meters. And lastly, let's say we measure something that's 22 meters. They're probably this dot over here. This is wrong. Okay, not accurate. It's nowhere near the right answer, and it doesn't show any level of precision. So we're over in this range on this side. All right, questions about accuracy versus precision. Again, it looked like most of you had a good understanding of it based on your daily question. So with this added visual, I'm hoping that we're doing pretty good on that. So when you read through your section 1.3 yesterday, a lot of the section talked about measurements, how to take measurements, how to write measurements, how to change measurements. This is the first pair of words that we're using just to describe measurements. Accurate measurements are close to the real value. Precise measurements are ones that show a lot of data. Recording measurements, then we've got a few different things that we can work with. First of all, every measurement that we work with should have units. What's the system of units that we're going to be using in this class? What is the system of units that we're going to be using? They were talked about in these sections. Zane. Metric. Now, even more specific than the metric system. What there was one talked about. Crud. Say, McKenna? Yeah. It is. Right. The SI system, which is the International System of Units. Why do we call it SI and not IS? Well, it's French. System International, and they put their adjectives after the word on that one. So the SI system, which is mostly the metric system. There are only a couple of things that we don't use from the metric system, one of which is temperature, which for some reason in the SI system we use Celsius rather than Kelvin. So that's one spot where we vary. But otherwise, we're going to be using the SI system. And we use the SI system so that we can make sure we're being consistent. So that if we take a measurement and a scientist in another country uses a measurement, we can agree on what units that can be in. There is, I'm not sure if it's a myth or if it's an accuracy, but there is a story about NASA putting together some pieces for, I believe it was the Hubble telescope, and some of the pieces when they got up to space didn't fit together. And the reason they didn't fit together is one group's measurements were in centimeters, while the other were in inches. And someone had forgotten to bother to convert between the two, and then they had pieces that didn't fit. Now, this part I know is true. The Hubble didn't work when it was originally put up. It was millions of dollars that they put into this thing, and it didn't work. They needed to have something corrected and had to add in an extra piece in order to get it actually to function. And supposedly, that's because somebody forgot to use the right system and didn't convert properly. So SI system is the one we're going to be using, and it is mostly metric. Okay? In the SI system, we have two types of units. We have base units, and we have derived units. What is a base unit? Give me an idea. What would a base unit be? Go ahead. Yeah. Meters, grams, degrees, seconds. Any of those are base units. A base unit's any unit that just measures one property. So meters, grams, liters, seconds. And a derived unit is a unit that takes any two base units and combines them. So it is made of more than one base unit. The one you guys probably use most commonly is used for determining speed. What's the unit you use when you talk about speed? Miles per hour, mph. So we're taking two base units, miles and hours, a base unit for distance, a base unit for time, and we're combining them into a derived unit. Well, we won't use miles per hour in physical science. We'll use the metric version, the SI version, meters per second, in order to show speed. We'll also be using ones for something like density, which we'll get to later today, which would be grams per milliliter or grams per centimeter cubed, grams per milliliter, showing that we have more than one dimension or more than one property about something that we're measuring. Okay? Questions on base versus derived units? Okay. So in addition to talking about units, we also talked about ways, or we read about ways in which we can write numbers. Now, I could write out a handful of numbers about different properties of the universe. So the mass of the sun is, let me see if I can get this right, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30 kilograms. Well, that was awful. I don't intend to do that again, which means that I need a better way of writing this number. Okay? One of the ways in which we can improve upon writing that number is by using something called scientific notation. Someone who did the reading, what is scientific notation? Kendall? Excellent. So a way of expressing a number as the product of a value between 1 and 10 and the product of 10. So I'm going to go ahead and take this number, and I'm going to act as though the decimal point is right there after the 2. So changing this to scientific notation, I have my first step, only one number is to the left of the decimal. Only one number is left of the decimal. 2. And she said it was the product of a number between 1 and 10 and a power of 10. So times product 10, and then I just have to count how many spots I moved the decimal. Anybody know how many spots I moved the decimal? 30. Yep. 30 kilograms. So I could write this in longhand decimal form, awful, or I could write the same number this way, 2 times 10 to the 30th kilograms. This is how we handle large numbers in astronomy. This is how we handle small numbers in chemistry, biology, physics. We use scientific notation to make sure that we don't have to write out things longhand and waste both time, space, and effort. Okay? Questions about scientific notation? I'm going to put 2 here. Multiply it by something to the power, or by 10 to a specific power. Multiply by 10 to the power of how many spots the decimal was moved. Okay, there's our first way that we could deal with writing numbers. Okay, the next way in which we could deal with writing really large numbers uses scientific prefixes or metric prefixes. So metric prefixes are going to be things like, let me get this lined up here, giga, mega, kilo, there's hecta in here, but no one ever uses that, centi, milli, and I'm going to put micro in here as well. Okay, so, and these are prefixes. Who's heard something use the term giga? What's it with it reference to? Gigabyte. A gigabyte is 1 billion bytes, and a byte is a piece of information on a computer. So giga means 1 billion. So if you use up a gigabyte of data, you are using up 1 billion bytes of information. Okay? Mega. Where have we heard mega? Megabyte. Absolutely. And mega is one step down from giga, and this is 1 million bytes. 1 million. So if you're using a megabyte of information, you're using 1 million pieces of information, 1 million bytes. Okay? Kilo. One step down even further. Well, if this was a billion, this was a million, what's kilo going to be? I heard it. 1,000. 1,000. All right, where have you heard kilo? Kilogram, I heard. Jack, I saw a hand. Kiloliter. Anything else? Yeah. Kilometer. Do we have any more? If you find really small measurements on your computer, kilobyte. Okay, so after that, we start talking about small terms. Small ones, we're no longer trying to say how many of the base unit go into it, but what fraction of the base unit is this made up of. Centi, where have you heard centi? All right, centimeter. What else? Centennial. Okay. What else? Cent. Where have you heard cent before? A penny. A penny is a cent. All right? So cent stands for 1/100th. 1/100th. What were you adding, Sekar? Centipede. So in each one of these, even though these aren't measurements over here, they're all standing for the same thing. They all use cent for the same reason. A centennial is 100 years. Centipede, it's a bug that appears as though it has 100 legs. Penny, a cent, it's 1/100th of a dollar. All of them are using the same idea. Milli, where have you heard it? Milligram. Different root on that. Nope, not quite that small. Yeah. Millimeter. Do I have any others? All right, and this is 1/1000th of a measurement. So if we're talking about our meter stick, and I've got 1 meter here, well, from the previous one, 1 centimeter, there's 100 centimeters to a meter, a cent. And if we have 1 millimeter, 1 millimeter is 1/1000th of a meter. So there's 1,000 millimeters on this stick. Okay? Last one, micro. Where have you heard micro? Microwave, microscope. Anything else? I like those two. All right, and this is 1/1,000,000th. Okay, so 1/1,000,000th, meaning you need 1,000,000 of a micrometer to make a meter, 1,000,000 of a microliter to make a liter, a million micrograms to make a gram. When we talk about microwave, we talk about microwaves because it takes 1,000,000 wavelength, or is it wavelength? The wavelength is, I'm sorry, the frequency is in the millions of times per second that it comes by. So if we were talking about a microwave oven is sending 1,000,000 waves per second in trying to heat your food. Okay? Microscope, we're talking about trying to see things that are on the order of 1/1,000,000th the size of a meter. We're trying to see things that are incredibly small. Okay? So if I go back to my mass of the sun, which of these terms do you feel like would be the most helpful? If I went back to the sun, which of these terms do you feel like would be the most helpful? Giga. Okay, so I'd probably use giga, though that still would be pretty large because I'd have 1, 2, 3, 4, 5, 6. I'd still have that many gigagrams. That's still a lot of zeros. So I'd probably stick to scientific notation on this one. However, something I could start talking about in terms of some of my prefixes, if I went to minutes in a year. So if I wanted to measure the number of minutes in a year, I would be talking about 525,600 minutes. That's the number of minutes in a year. So which of these terms do you feel like would be the most appropriate for measuring number of minutes in a year? Yeah, Colin. Why kilo? Why kilo? That makes sense. Okay, so if I wanted to change this so that I could measure it in the thousands, a lot of us know the trick where you just move the decimal over, right? Well, you can use that to check your answer, but I want to show you another technique called dimensional analysis that you can use just the same. So if I have 525,600 minutes, I'm going to multiply it by a fraction. And the point here is that I want to show that I'm manipulating the units. So if I want to get rid of minutes, I'm going to put minutes in the denominator of my new fraction so that it'll cancel out. In math, if you have something in the numerator and something in the denominator, we understand that those should cancel each other out. Yes? That's something we've worked with fractions. Okay. In the numerator, I'm going to write the unit I'm trying to change it to. Colin said I want to use kilo, so I'm going to have kilominutes. Okay? How many minutes would be in a kilominute? There should be 1,000. 1,000 minutes to 1 kilominute. So 1,000 minutes make up 1 kilominute. Make sense? Okay. And now if I want to know how many kilominutes I have, I just have to punch this into a calculator. Okay. It's pretty easy to actually do that one in our head for a lot of us. But if you've got a calculator, go ahead and pull it out. The next one is not going to be easy to do in your head. Okay. So this answer comes out to 525.6 kilominutes. I'm abbreviating. Okay. Questions on that one? Okay, let's take a try a different one. Try one that's a little harder that you can't do in your head. I want to know exactly how many years that is. Okay? So 525,600 minutes. If I'm trying to change that to years, what unit should I go to first? Hours, that makes sense. So I'm going to multiply by fraction bar. What unit should I put on the bottom? Minutes. Why minutes? I heard it. I'm canceling it out. What goes on top? How many minutes in an hour?
60.
Everyone should be able to answer that. Okay, after I've changed it to hours, what would I want to try to change it to next? Days sounds good. Times. So what unit, not what number, what unit do I put in the denominator? Hours, because I'm trying to cancel it out. What unit do I put in the top? Days. How many hours to a day? And lastly, if I'm trying to change to years, what unit do I put on the bottom? And what unit do I put on top? How many days in a year? 365. Except on leap year, correct? Okay. Leap year is the year where we add one extra day because the actual amount of time that it takes for the sun, or sorry, for the moon to go around for the Earth to go around the sun, there's what I want, is not exactly 365 days. It's 365.25 days. So we add in one extra day every 4 years to keep on track. Otherwise, our seasons would start to migrate around the calendar. All right. So, grab a calculator, punch this out, find the answer. We are going to be working with density for the next couple days, and it is actually going to be our lab that we work with on Friday. So we want to make sure that we're able to handle density in terms of making accurate and precise measurements. We want to be able to state density in terms of appropriate base units. And if we need to be able to convert some of these larger units into appropriate ones so we can calculate density. So we're going to do a quick example on density after I get a definition here. So from someone who read the chapter, what is density? From someone who read the chapter, what is density?
The ratio of an object's mass to its volume.
Perfect. So the ratio of an object's mass to its volume. So we can actually restate that statement as an equation, where density is equal to mass over volume. All right, math in science. In this class, in physics, in physical science, and I'm pretty sure in chemistry, we will never ask you to memorize an equation. Memorizing equations is a waste of brain space. Being able to understand how to interpret an equation is not a waste of brain space. So while I will write on the board D equals mv, you have to know that D stands for density, M stands for mass, V stands for volume. Okay? Where are my individuals who are in algebra right now? Okay, and geometry? All right, so you guys, I expect you to be able to take this equation and solve it for different variables. Okay? So geometry, especially you guys, you should be able to look at this and say, I know how to solve for M. I know how to solve for V. Okay? If you are not in algebra or geometry, then I am not expecting you to be able to solve this for different variables. And we can do that real quick here. So if I have my base equation and I want to find mass, Well, I can multiply variables just like I multiply numbers. If I want to solve this for, if I want to solve this for mass, I would multiply both sides by volume, and I'd have density times volume is equal to mass. If I wanted to then solve this for volume, I could divide both sides by density and show that mass over density is equal to volume. Okay? So I'm going to just highlight my important ones here. Okay. And if you are not in either algebra or geometry, I will write these out for you. If you are in algebra and geometry, then I'm going to be able to expect, definitely from geometry students, that's all I'm giving you. Algebra students, I have to find out where you guys are. Okay? So if I wanted to say find the density of my calculator, I would need to measure two things. What things would I have to measure? Mass and volume. Yeah, absolutely. So first one I'm going to measure, mass. Come over here to the scale, and the mass of my calculator is 247 grams. Okay, 247 grams. 247 grams is mass. Okay, next up, I'm going to need to measure volume. I'm going to approximate my calculator as a rectangular prism. So I'm going to take length times width times height. Length is 18 centimeters. Width is 2 centimeters. Height is 8 centimeters. So I said 18 by 2 by 8, correct?
Yeah.
And those are all in centimeters. So someone with a calculator, other than me, what's the volume of the calculator? Yeah, what'd you get? 288. Can anyone confirm his number? Meaning someone who has also done the calculation agree. Perfect. 288 what? Cubed. Because I multiplied a centimeter by a centimeter by a centimeter. 3 of them. Okay? So now I can use this in my equation. D equals mass, 247, over volume, 288. And I can calculate that to find what as the density of my calculator. What is the density of my calculator based on that? I see calculators around there, so somebody do the math real quick. What'd you get? 0.86? Anybody agree? I got 2 thumbs up. Excellent. 0.86, and I'm going to use the same units here. So if that was grams, and this is centimeters cubed, I'm going to create the derived unit of grams per centimeter cubed. Okay? Questions on how I found the density? Okay, on the Google Classroom, there is a worksheet on calculating density. I would like for homework tonight you to do the first 2 problems on it. We will spend time in class working on the remaining 8 tomorrow.